An exciting day here in the W2 AEW lab. We have a big box here from Tektronix, and this is a new RF signal generator for the bench. So we'll do a quick little unboxing and show you some of the basic features of what this RF signal generator has to offer, and try to figure out how to make room on the bench over here so we can use this in future videos. Alright, let's cut this baby open here. Box inside the box here. And of course here we're going to have the power cord, the RF cable, end connector to end connector, and the frequency response of that cable. And we've got the packing list, the user manual, and installation and safety instructions, and calibration documentation, and user documentation on a CD. Okay, let's lift this baby out of here. And so we get this box out of our way. Put that off to the side here for the moment. And let's see what we have for the signal generator. Take off the styrofoam pieces and the plastic wrap. And there we go. This is a brand new Tektronix TSG4106A, a DC to 6 GHz RF signal generator. RF output here, and then DC to about 60 or 70 megahertz on the BNC connector here. And there's a whole myriad of connectors on the back. So let's take a closer look at all the inputs and outputs and the user interface, and put this baby on the bench. A quick look at the front and rear panels. Front panel's nice and clean. It's a color display we'll look at in a moment. Two connectors for the RF output. The LF output takes you from DC up to either 62 megahertz or about 90 megahertz depending on the model. For the 6 gigahertz model that goes up to 90 megahertz. And then the RF output takes you from about 950 kilohertz up to the maximum frequency range of the instrument, which in this case is 6 gigahertz. So these are soft keys that will work with menus on the display, your typical numeric keypad, and quick entry keys for setting frequency, amplitude, and getting to the modulation. A USB port allows you to quickly load and save setups and waveforms. Let's take a look at the rear panel. The rear panel has a lot of connections on here, IEEE 488 bus, RS-232 bus, as well as a LAN port. There are input and output here for the reference time base. This unit has got an ovenized reference, so it's a very, very stable reference, so you most likely use the output here to become the reference for other instruments in the lab, but you do have the ability of tying in an external reference if you've got that in your lab and you want to tie this to that. Analog modulation in and out. And then this also features vector modulation, so the baseband quadrature I and Q inputs can be put into here to quadrature modulate the output. 200 megahertz of bandwidth or so on each of the I and Q, which gives you about 400 megahertz of RF modulation bandwidth with that option. And then when you're using, say, internal quadrature modulation, like a 16 QAM or something like that, the I and Q that are used internally are also available on the back here to go into a scope or do further analysis. When sending digitally modulated RF data or arbitrary modulated RF data using the IQ generator, you can get a symbol clock and various event outputs that can be programmed to come out at certain times during the waveform that you're playing out. So a lot of flexible IOs on the back panel. Alright, so let's power it up and take a look at the interface and how you drive this instrument. Okay, pretty straightforward. You turn the RF output on or off with a simple push button here. You can set the frequency just by dialing in a particular frequency here. Set the amplitude. The amplitude can be adjusted from plus 16.5 dBm all the way down to minus 110 dBm. So a lot of output adjustable range to test receivers and circuitry and things like that. A push and hold on the preset brings you back to just a kind of a preset condition. And setting up modulation is just as easy. I could either hit the modulation key here or the soft key down here to bring up the modulation menus. The first button here allows you to select the modulation type, whether it's an analog modulation such as AM, FM, or PM, or a pulse modulation. And you can simply use the arrow key to move over and then scroll down and select the one you like. You can move back. We select vector modulation. That allows us to select, ASK, FSK, QAM, etc. And there's a couple of standard presets. So very simple to go and set the various modulation parameters. Once you pick a particular modulation type, let's say we pick AM, the rest of the menus will change to allow you to adjust that. You can pick the baseband source, which could be an internal source, sine wave, ramp, triangle, square, noise, or an external source or a custom waveform that you load in. Once you decide that, you can then select the rate, which would be essentially the baseband frequency. In this case, it would be a 50 kilohertz sine wave, and then for AM, modulation depth. If we select something like FM, then we can see that that changes from depth to deviation, because that would make sense for a frequency modulated signal. All the same other choices. If we go back to, say PM and select that, then we get phase deviation instead of frequency deviation. Now the optional vector modulation allows you to select amplitude shift keying, frequency shift keying, and again the menus will change depending on what you want to do. Let's say we picked FSK, then we can pick the constellation or the number of points. It defaults to a 4 FSK, but you can pick binary frequency shift keying 4, 8, or 16 FSK, and again pick the source, whether it's going to be a pseudo-random binary sequence or a data pattern or some custom pattern. And then you can select the filter type for the baseband signal, which will determine how quickly we're shifting from one of the frequency states to the next, which also affects the occupied bandwidth of the signal. And there's some more parameters on a second page to set the symbol rate of the digital data that is being used to modulate the data, or the RF, set the deviation, set the pseudo-random binary sequence length. Those menu items are basically pretty much the same for most of the vector modulation types. We pick, say, a QAM modulation, then we have a choice of QPSK or 4 QAM, 16, 32, 64, 256 QAM, or a custom, and then the same choices for the baseband data source, the filter, symbol rate, and symbols and things like that. Alright, let's just set up a signal here at, let's say, 145 megahertz carrier frequency. And I'll turn that RF output on. Let's set up the spectrum analyzer here to a center frequency of 145 megahertz, maybe a span of, maybe 10 megahertz or so. And we can see our CW unmodulated signal here. Let's play with some modulation. So let's go to modulation. Let's change the type of modulation to AM. We'll select that. Do a 50 kilohertz sine wave at 50% modulation depth. Turn the modulation on. And we can see the sidebands come up here. Let's knock our span down to, say, 1 megahertz. Now we can actually see the modulation sidebands. There's our carrier. There's the upper and lower sideband for the AM signal. And we can see there is some harmonic distortion on the baseband signal, but it's a good about 40 dB down. So that's perfectly fine. Now with the MDO here, we can actually look at the amplitude versus time variation of that RF signal. So if we go and select RF versus time traces, turn on the amplitude versus time trace, and we can actually see there's our sinusoidal amplitude variation that we set up on the signal generator. If we change our source to, say, a ramp, let's turn that on. Let's see the spectrum changed here, and there's our modulation shape. Let's bring that back to, say, a sinusoid. Turn that back on again. Now, one of the outputs that was available on the rear panel was the analog modulation out, or the baseband output. I've got that tied into channel 2 on the scope here, so if we turn that on, there we can actually see that's the actual baseband signal being generated by the signal generator that's being used to modulate the signal for this AM modulation. Now, of course, if we change, say, the modulation depth from 50% down to something like 10%, we can see the amplitude variation has dropped down, and our sidebands have dropped down, as you would expect. Let's change the modulation type from AM to FM. And now with FM, we can see the modulation sidebands, and it's normal to have sidebands spaced, at the baseband frequency, and the amplitude of each of those is going to be determined by a set of Bessel functions. I've got a video on that I'll link down below if that's helpful. Now, of course, the amplitude is not changing over time, so the amplitude versus time trace isn't going to show us anything. So if we turn that one off and turn on our frequency versus time trace, then I'll just adjust the position of that and the scale of that, and we can see that basically has the same shape. Now for FM, it's interesting to watch the sideband magnitudes as you change the modulation index. So in this case, if we leave the baseband frequency alone and change the deviation, we can actually see these sidebands coming up as I bring that up, and the carrier actually falling. Okay, we can see our frequency deviation versus time is changing, so I'll adjust the scale on that. Let's keep turning our deviation up, and we can see the carrier actually can drop out, and it's actually a interesting way of measuring frequency deviation is by adjusting modulation index until the carrier gets nulled out. It's a very accurate way of determining modulation depth. Alright, so let's play with some of the vector modulations. Let's start off with, say, vector modulation. Let's pick, say, an FSK. And we'll do just a binary FSK, so it'll shift between two different frequencies. The source, we'll just use a PRBS, is fine. We'll leave the filter as a rectangular filter, so it's easy to see the frequency snapping from one to the other. We'll set the symbol rate. Let's go to, say, 1 megasymbol per second, so we'll change it at 1 megahertz rate at the max based on that PRBS data. And let's change the deviation to, say, 2 megahertz or so. Okay, so now we'll go from a single carrier here at 1 gigahertz, turn the modulation on, and we can actually see the spectrum. If we go to our RF versus time traces, turn on frequency deviation versus time, now we can literally see the frequency deviation versus time for that modulation. Now the vector modulation uses the I and Q, or quadrature modulation, so we can actually turn on the I and Q signals. Now for an FSK, what will happen is we're going to have I and Q kind of running at the deviation rate, or 2 megahertz, but the phase between them is what's going to determine whether the frequency is low or high. In fact, if we do a single shot capture, we can actually see this. Let's zoom in a little bit. Okay, and we can see that when the frequency deviation is above the center frequency, we can see the phase relationship between I and Q here and here, that this one, which is I, is leading Q, and then we switch to low, say like in this case here, now the Q is leading the I. So you can actually see the phase shift happening here and here, where we're slipping the phase back and forth between I and Q when we're modulating between a positive deviation and the negative deviation from center. Let's switch over to a QAM type modulation. So let's pick vector, and let's pick QAM modulation, and we'll use a QPSK, or a 4 QAM, and we'll still use a PRBS pattern. We'll leave a rectangular filter so the phase changes are nice and snappy. It's going to occupy a lot of bandwidth, but that's okay. Let's set the symbol rate to 1 megasymbol per second, and let's turn the modulation on. Okay, now we can actually see it's unfiltered, so we're occupying a lot of bandwidth. If we change the filter, the bandwidth would change. We can see the I and Q data waveforms here. In fact, if we do a single capture, the I and the Q look like NRZ data patterns, if you will. And there's 4 combinations, both low, both high, and then the combination of one or the other, and that corresponds to the 4 phases of QPSK. In fact, if we go to our RF versus time traces, let's go and turn on phase versus time, we can actually see the 4 different phase steps that the carrier is going through and how they correspond to the 4 conditions of the I and Q waveforms. Well, as you can see, this RF signal generator, it certainly has a lot of features, and we've only just touched on them here. So it's going to get a lot of use down here, and I guess the only problem that I can see, I can kind of summarize by paraphrasing a movie from 1975. I think I'm going to need a bigger bench. See you next time. Oh, we're getting a visit from Sophie the lab dog.